This tower has not lost power. Its massive cooling system has not shut down. No alarm is sounding anywhere in the building. To the wealthy tourists sleeping in the luxury suites above everything, feels completely normal. But somewhere between the blistering desert outside and the pristine apartment inside, the volume of fresh air moving through these ducts is slowly dropping. To understand the hidden pressures on Dubai, we must look beyond the empty hotel rooms or the shifting tourism numbers. We must look at the invisible machinery keeping the entire illusion alive. In one recent engineering experiment, severe filter clogging reduced the net supply airflow of a mechanical system by 37%. The strangest part was that the electricity use did not necessarily rise to warn anyone of the failure. A system can continue to run while its actual capacity to breathe slowly suffocates. When does a protective filter stop being a shield and become a solid wall? To answer that question, we first have to see how a completely sealed skyscraper actually interacts with the outside world. The global tourism brand of Dubai is built on the promise of absolute effortless comfort. Millions of international visitors arrive expecting a flawless environment, regardless of the extreme natural climate, waiting just outside the glass. A skyscraper does not defeat the desert simply by closing its windows. It survives by constantly processing the outside atmosphere before allowing it into the inhabited spaces. This means a sealed building is never truly disconnected from the harsh environment around it. It just transfers the responsibility of breathing from open windows to massive mechanical lungs hidden in technical floors. The local municipal regulations clearly mandate that buildings must possess adequate ventilation systems to maintain indoor air quality. These regulations prove that the authorities know exactly what is at stake. Equipment must be regularly inspected and cleaned because the atmosphere is inherently hostile to delicate machinery. But maintaining this artificial climate requires a continuous, immense effort. The polished promotional videos showing endless glass facades leave out a crucial operational reality. Every single cubic meter of air that cools a luxury hotel lobby or a high-rise apartment had to be pulled from a dusty sky. This creates a permanent physical link between the unpredictable desert and the heavily controlled indoor oasis. If we want to find the exact point where this system begins to experience severe stress, we cannot just look at the financial reports. We have to follow the physical journey of the very thing the city is trying to keep out. What exactly enters the system when a building takes a deep breath? The most visible particles in a desert environment are not necessarily the ones that cause the most profound systemic damage. Large grains of sand are heavy, and they tend to settle quickly on the ground or bounce off the exterior louvers of a building. The more persistent intruders are the ones that are far too small to see with the naked eye. Fine particulate matter can remain suspended in the air for extended periods, traveling vast distances on regional wind currents. When the massive mechanical fans of a high-rise building activate, they pull this invisible ocean of particles directly into the intake vents. Research conducted on residential units in this region demonstrates that fine particles easily infiltrate indoor spaces, depending on the ventilation pathways and the tightness of the building envelope. It is important to note that not all indoor pollution comes from the desert. Cooking and cleaning and the simple presence of human occupants also generate significant particulate matter inside the rooms. But the fundamental purpose of the heavy-duty mechanical filtration system is to act as the primary defense against the immense outdoor volume of dust. The filters are designed to capture these microscopic threats before they can foul the sensitive cooling coils or enter the lungs of the tourists. The size of the particle dictates exactly how deep it can penetrate the building infrastructure. These microscopic fragments of the desert are drawn into the dark metallic corridors of the ductwork at high velocities. They rush toward the first major mechanical barrier. Filters exist precisely to catch these particles and protect the fragile ecosystem behind them. So where does the problem actually begin? At first, the system appears to be winning the war against the environment. A newly installed filter acts as a highly efficient physical web, capturing millions of particles upon contact. The air flowing out the other side of this barrier is significantly cleaner. The expensive cooling coils remain protected from abrasive damage and thermal insulation loss. The luxury apartment remains perfectly isolated from the dust storm raging outside the windows. The hotel guests can look out at the hazy skyline while breathing deeply in a perfectly controlled microclimate. To anyone walking through the grand lobbies or dining in the premium restaurants, the building is performing exactly as intended. The technology is doing its job, and the heavy investment in mechanical infrastructure seems entirely justified. But there is a fundamental law of physics that cannot be ignored in this relentless environment. Every single particle captured is a particle prevented from entering the room, but it is also a particle that now remains permanently trapped inside the mechanical system. The dust does not just magically vanish once it touches the synthetic fibers of the filter media. It stays there, and it slowly builds a new physical reality within the machine. The filter does not become a severe problem because it fails to catch the dust. It becomes a hidden operational burden precisely because it catches so much of it. As the days and weeks pass, the accumulation of dust begins to alter the physical properties of the filter. The initial layer of captured particles creates a foundation for the next layer to attach to. This process is known as dust loading, and it fundamentally changes how the entire air handling unit operates. When the filter is brand new, the air passes through the clean fibers with minimal resistance. The pressure difference between the front of the filter and the back is very low. But as the dust forms a thick, continuous cake across the surface, the system experiences a rising pressure drop. Imagine trying to breathe through a piece of cloth while someone slowly adds layers of fine sand on top of it. The physical effort required to pull the same amount of air into your lungs increases dramatically. In a mechanical system, the fans are the muscles trying to pull the air through that increasingly dense barrier. According to established engineering principles, the field performance of a filter can differ significantly from its clean laboratory rating. The operating time, and the dust load, and the specific system configuration all influence the actual resistance encountered in a real building. The resistance grows silently in the dark technical rooms, far away from the polished guest areas. The building is slowly fighting a harder battle just to maintain its baseline function. But not every fan responds to this rising physical resistance in the exact same way. When the filter becomes heavily loaded, the building enters its first stage of invisible failure. There are generally two ways a mechanical system reacts to this intense pressure drop. In the first scenario, the system tries to compensate by forcing the fans to work much harder. The fan motors ramp up their speed to push the required volume of air through the thick layer of dust. This reaction increases the electrical load and places significant mechanical stress on the moving parts. The equipment begins to operate closer to its absolute physical limits, which can shorten its operational lifespan. In the second scenario, the system simply cannot compensate for the extreme resistance. The fan continues to spin at its normal rate, but it is unable to move the same amount of air. The total airflow volume drops silently. This means the amount of fresh outside air being introduced into the building decreases. The ability of the system to dilute indoor pollutants like carbon dioxide and chemical emissions is severely compromised. A tourist might be sitting in a premium suite, paying top rates, while the actual quality of the air they are breathing slowly degrades. The room might still feel comfortable on a superficial level. But if the temperature were still correct, would anyone even notice that the apartment was receiving far less fresh air? This silent reduction in ventilation is the true hidden cost of the desert environment. And this is exactly where the electricity reading on the building management system can become incredibly misleading. We often assume that a struggling system will always consume more power, but data from controlled mechanical experiments reveals a much more complicated and surprising reality. In a detailed study published in 2025, researchers examined the impact of severe filter clogging on ventilation performance. Under heavily clogged conditions, the system experienced a 37% reduction in net supply airflow. Furthermore, the exhaust air transfer ratio increased significantly from 7% to over 17%. This means the balance of the entire air distribution system was fundamentally altered by the dust. But the most crucial finding was that the electricity consumption did not necessarily spike in the way an operator might expect. If a fan is moving 37% less air, it is doing significantly less physical work. Therefore, it might actually draw less electrical power even though the filter is completely choked. A falling power reading on a control screen can easily resemble increased operational efficiency. A facility manager looking at reduced energy costs might think the building is performing brilliantly. But if the fan is moving less air, The building is simply doing less of the job it was originally designed to perform. The residents and the tourists are the ones absorbing the deficit through lower indoor air quality. The illusion of efficiency hides the reality of mechanical starvation, but massive dust accumulation is not the only way a filtration system can fail its inhabitants. Sometimes the dust never even touches the filter media. A building might purchase the most expensive high-efficiency filters on the market to protect its indoor environment, but the effectiveness of a filter is entirely dependent on the integrity of the physical frame holding it in place. If the frame is slightly warped, or if the rubber seals are degraded, the air will instantly seek the path of least resistance. Instead of pushing through the dense synthetic fibers, the high-velocity air will simply squeeze through the tiny gaps around the edges. This phenomenon is known as filter bypass. It allows raw, unfiltered desert dust to stream directly into the clean side of the mechanical system. These abrasive particles then collide with the wet cooling coils, creating a layer of insulating sludge. Field investigations often show that laboratory efficiency ratings overestimate actual performance because they do not account for these installation realities. A poorly sealed high-grade filter can perform worse than a perfectly sealed low-grade filter. The most troubling dust in a luxury skyscraper may not be the dust you can see trapped on the filter surface. It may be the dust that bypassed the defense entirely and is now circulating freely through the ductwork. The system is failing, but it leaves almost no visible evidence of its failure at the point of entry. Meanwhile, down in the luxury apartment, the tourist walks over to the wall and looks at the digital thermostat. The screen brightly displays 22 degrees Celsius. The air blowing gently from the ceiling vent feels sufficiently cold. Because the temperature is perfectly maintained, the resident assumes that the entire HVAC system is operating flawlessly. But temperature is only one fraction of the overall mechanical equation. Cooling the air and dehumidifying the air and actually filtering the air are distinct processes. A system can successfully chill a room while simultaneously failing to deliver adequate fresh ventilation. Studies on indoor particulate matter confirm that outdoor dust infiltration depends heavily on ventilation pathways and building design. The thermostat on the wall does not display the particulate matter concentration. It does not show the hidden filter bypass or the severe pressure drop in the technical room. It offers a comforting illusion of complete environmental control. This creates a profound psychological disconnect between the perception of luxury and the physical reality of the air quality. The brand of Dubai relies entirely on this perception remaining unbroken. If a visitor pays thousands of dollars for a premium experience, they expect perfection in every breath. Would anyone judge a 5-star apartment purely by the number on its thermostat or by what is actually entering their lungs? When the hidden pressure finally becomes too great, the solution seems incredibly simple. A technician opens the heavy metal doors of the air handling unit and follows the strict safety protocols to isolate the equipment. They pull the dark, heavy filter out of its metal rack and immediately dispose of it. They inspect the rubber seals and slide a pristine white filter into the slot. They check the pressure gauges and verify that the airflow has returned to its optimal design parameters. For a brief moment, the system is fully restored and the problem appears to be entirely solved. The building is breathing easily again, and the defense is back in place. But this simple act of maintenance immediately raises a much larger and more difficult question. Replace it when? Building operators must decide whether to replace filters based on a rigid calendar schedule, or based on visual inspection, or based on live pressure data. A filter that looks dirty might still have plenty of usable life before it causes a restrictive pressure drop. A filter that looks relatively clean might already be restricting airflow if the particles are buried deep inside the fibers. The local regulations require systems to be kept clean and maintained according to technical guidelines. But replacing filters perfectly on time across a massive skyline is an incredibly demanding logistical challenge. The temporary relief of a new filter is just the beginning of a relentless cycle. This continuous cycle of replacement reveals a critical economic fault line deeply connected to the broader tourism industry. Dubai has built its economy on attracting massive numbers of international visitors to its spectacular hotels and retail centers. But the financial success of this model is highly vulnerable to regional instability and global economic shifts. When a tourism crisis hits, or when aviation disruptions slow the flow of passengers, the hotel occupancy rates begin to fall. The revenue generated per available room experiences severe downward pressure. However, the intense physical cost of fighting the desert does not care about the economic fluctuations. The filters still clog with dust. The technicians still need to be paid to inspect and clean the equipment. The electricity is still required to push the air through the heavily loaded mechanical lungs. The supply chain of replacement materials must remain constantly active. If a hotel tries to save money by delaying maintenance during an economic downturn, they risk destroying the very luxury experience they are trying to sell. Delayed maintenance leads to higher pressure drops and filter bypass, and reduced fresh air for the guests. This is the ultimate maintenance trap. The city must spend heavily just to maintain the baseline illusion of a pristine environment. When growth slows down, these fixed operational costs become a heavy anchor on the profitability of the entire real estate sector. Dubai definitely knows how to filter the dust perfectly. The true problem is that the expensive act of filtering never actually ends. When you step back and look at the entire city, the sheer scale of this vulnerability becomes staggering. We have followed the journey of a single dust particle into a single filter inside one mechanical room. Now multiply that continuous physical struggle by thousands of high-rise towers and massive shopping malls. Think about the endless mechanical floors operating 24 hours a day above the glowing skyline. The habitability of this entire urban model depends completely on a fragile, invisible chain. Outdoor air must meet the intake vent and pass through the filter and be pushed by the fan and cooled by the coil. The sensors must read the data, and the maintenance crews must respond without hesitation. If any link in this chain breaks, the desert immediately reclaims its territory. The primary vulnerability of the city is not that one specific filter might clog during a bad storm. The danger is that every single sealed building in the city requires this chain to be powered and renewed without interruption. This is a massive ongoing tax levied by nature itself. The real estate market and the hospitality sector must constantly outpace this baseline cost just to remain profitable. Can a building actually be designed to be smarter than the dust storms that surround it? The industry is slowly shifting toward better technological solutions to manage this endless burden. Operators are increasingly installing advanced sensors to measure real-time pressure drops across multiple filtration stages. They are monitoring actual airflow volumes rather than simply checking if a fan motor is turned on. By placing particulate matter sensors both before and after the filter racks, engineers can detect bypass leaks before they ruin the cooling coils. Implementing predictive maintenance based on actual dust loading can optimize the replacement cycle and save significant labor costs. Some designs incorporate multiple stages of filtration to distribute the burden and extend the life of the most expensive media. But all of these technological advancements come with a strict conditional reality. Sensors do not physically replace clogged filters. Software cannot climb into a dark duct and repair a broken rubber seal. Data is entirely useless if the management team does not have the budget to deploy human labor to fix the problem. None of these innovations eliminate the fundamental need for continuous physical maintenance. Dubai can absolutely keep the desert outside its luxury towers, but it can only do so by aggressively pulling its air through machines that are never allowed to stop. The deepest threat is not that a sudden massive storm will suffocate a skyscraper overnight. It is that every microscopic particle captured becomes a permanent part of a maintenance burden that never disappears. The spectacular towers may look completely sealed from the harsh reality of the desert. In reality, they are breathing heavily through it every single second. The polished image of a flawless future city is a powerful tool for attracting global wealth. But underneath the marketing brochures and the record-breaking tourism statistics lies a mechanical reality bound by the laws of physics. The cost of defying extreme geography is not just the initial billions spent on construction, it is the daily unseen labor required to force the environment into submission. A skyscraper in the desert is a spectacular machine that must run perfectly just to stand still. The system can endure the pressure, but only as long as the revenue keeps flowing in to pay the maintenance bill. When the silent machinery begins to struggle, the luxury experience is always the first thing to erode. This documentary examines documented filtration and ventilation mechanisms relevant to mechanically cooled buildings in dusty climates. The cited engineering experiments and particulate matter case studies do not establish that every high-rise building in Dubai is experiencing severe filter failure. Performance varies significantly by architectural design and maintenance strategy and local environmental conditions. This analysis explores broad operational pressures and is not intended as personalized travel or financial advice. The economic correlations discussed are systemic observations based on public data available at the time of research. The physical challenges of the environment apply to all infrastructure operating in similar regional conditions. If the hidden systems operating silently behind the skyline interest you more than the polished tourist brochures, make sure to subscribe. In our next investigation, we will follow another invisible dependency, keeping a fragile economic model alive.